Hi folks, in this tutorial I would like to perform a modal analysis for a shear frame structure which is modeled with beam elements, and it is used to replicate the steps that are created by the YouTuber below in the ABAQUS CAE, but I'll be repeating those in the 3D Experience Release 2024. These tutorials are intended for people who are familiar with the ABAQUS CAE, or they're entirely new to the 3D experience, and either way, they would like to use the software capabilities. The finite element solver in the 3D experience is actually the ABAQUS program. Now, I select problems which are entirely done in the ABAQUS CAE, and the steps are uploaded in the YouTube videos, such as the one that you're looking at. The shear frame that's going to be considered consists of the following configuration. At the bottom of these two beams or columns or clamp, and the beam or the roof is modeled entirely as a rigid body with its mass specified at the center of uh, the uh, the beam on the top. Okay, the cross section of these beams is given as zero point 0.4 meter by 0.5 meter. The dimensions are given like so. And based on the density that's going to be used here, is that the mass of this floor is actually 25,484. It's just the volume of that top floor multiplied by the density of it. Now, as far as the beams is concerned, these columns are concerned, we are going to reduce the density of it by 10,000 times so that it actually does not affect the natural frequency calculation when it's done as a lump system, such as what you're seeing here. Okay. Now, the steps that I'm going to be following, I will create the frame structure in a sketch, and therefore because of that I actually have to join it. Otherwise, if I did it as a wireframe, lines in space, etc., that joining may not be necessary. It's not necessary. There are other ways of doing the process. Okay, so the YouTube video that I referred to uses the beam 32 elements. These are three-dimensional beam elements with a quadratic variation. However, this element is not available in 3D Experience, so I use B31, and the size of the beam element is about 200 millimeter or 0.2 meter. The calculation done by the YouTube reference predicts the first 6 frequencies in hertz to be as shown here, and we're going to be comparing our results with this set of values. Okay, so let's go ahead to 3D Experience. We'll start with the part file. Here's a part file. Okay, so on the vertical plane, I will sketch a shape that represents that frame structure. Change the dimensions later on, so something like that. Okay, so as far as the dimensions go, this is 3,000 millimeters, or basically 3 meters, 3 meters. All right, so it did scale the other side too. And this is actually 6,000 millimeter or 6 meter. Okay, so geometry is here. All right, exit. And I will join the sketch because of the way I'm doing it. It needs to be joined. So the join is in the operation that is available in the generative shape design. So here's a join icon. You select that sketch, and it's now joined. Okay, so we now go back to properties. Okay, so actually we can apply properties right here. So we go to tools, we create a property, create material. I'll call this tutorial 1, shear frame. Shear frame. Okay, let's create it. And now that once it's generated, I'm going to apply it right there. So apply, I'm going to close that, apply to that part. And now we're going to input the values. So we go here, double click on it, structural, ABAQUS multi, on the general option, density, we're going to specify it, but it's going to be that Dummington density, 0.24. It's 10,000 times smaller than the actual density, so that the columns, the mass of the columns don't enter the problem. Because we solve this thing essentially as a single degree of freedom system. And then we go to mechanical, elasticity, elastic, and the Young's modulus is 30 GPa. Okay, Poisson ratio is 0.33. Good. Okay, that takes care of the geometric model. Let me quickly save this. And now I'm going to go to the meshing module, which is a structural model creation, MTFEM. Oh, you know what? One thing I forgot to do was to create the orientation point here, because the cross section is not circular. It needs to be oriented. So I forgot to do that. While we're here, let's go back to the 3D shape right there, back there before we mesh it actually. You can see that. And then we're here, while essentials, create a point. And the point is, I'll make it, let's say 400 in the x direction. Right there, you can see that it's right there. Okay, the point is right here. All right, good. And if you want to see it better, you can make this thing actually maybe 1,000 so that you can see it better. 1,000. Okay, good. So back to finite element model, back to the meshing. Now we do beam measure. So because we joined this thing, when I select this, the whole thing is going to be selected. And 200 millimeter, the size of the element, and it is going to be, we will see that it will be actually B31 later on. Okay. So we say fine. It is meshed. And to confirm that it is meshed, here's what you can do. You can go to display under element shrink. If you select this tab and bring it down, the size of the element will be seen. But maybe I should hide the join. Yeah, now you can see it. You see that? See the size of the element? So that many elements, okay? And we say fine. Let's bring the joint back into the mode, show mode. All right. Okay, now the properties. For properties, first we define the cross section of the profile of the cross section. So here is the profile beam, and it's going to be a box. Oh, not a box, a rectangle actually. What is that? A rectangular. In the direction 1, 400 millimeters, and in the direction 2, 500 millimeters. Okay. That's the profile of the cross section. Now we go and do the beam section. We select the joint. On the profile, we select the profile 1. And for orientation point, this point. Okay. It's kind of hard to see how the cross section looks like. Actually, it looks like this. Okay. You can see that. but I can change the rendering so that you can actually see the shape. Let me go back to this slide and yeah, 500 this way, 400 that way. In other words, it should be thinner in the direction, if this is direction X, thinner in the direction X. Let's check it out. And it looks like it is thinner in the direction X. We say okay. Now, that takes care of this. Let's update it. Let's see under the display, display option, we can say, okay, right now beam rendering is none, so show it to me as a solid. You can see that, and you can see that this way that does not quite agree with what I have here. So well, let's keep it like this. If necessary, we're going to come back and change this so that it looks exactly like what you want. But anyway, so let's leave it like this for now, and we're done. So we can say that just show it to me as a sketch right there, or as none. All right, good. So now we're going to go to the final element module, which is structural scenario creation, because you're doing a simple frequency calculation. Oh, I forgot to put the mass. I forgot to put the lumped mass there. Cancel that. So we have to before we go to the scenario creation, we're going to go to our connections. Okay, we're going to say there is the rigid connection. You select this edge. Okay, so for the support one, I selected that edge, and for the support two, I right click, create support, create a point. And the point, well, obviously it's going to be this edge. Okay, cancel that. Let me show you what happened here. So right click, create a support, create a point, select this edge, and you're going to put a coordinates of, for example, what is that, x0, this is 0.2, x0, let's make it x0, y of 3000, and z of 3000. So it's right there. You can see at that location. You say okay. All right, let me update this and click on the abstraction tab and put a point mass, point inertia on that point that you just created, and the value of it is 24,000. What was it? 25484. 25484. 25484. And it's a lumped mass. That's there. Okay, now we're going to go to our finite element module, which is structural scenario creation. Select the finite element model that you created. Okay, so procedure is going to be frequency. That's this one, frequency step. 10 modes, okay, 10 or 6. I think we need only 6, so because we can compare it with, I'll just leave it as that. That's the default. Say okay. The bottom of these two are clamped. These 2 points are clamped, so you go to boundary condition. You select this thing as either fix, all 6 degrees of freedom checked, or clamp. Either way, makes no difference. So I'll do fix all 6 degrees of freedom restraint. 1, 2, 3, 4, 5, and 6. We say okay. And that's pretty much it. There is no load or anything. So let's go ahead and go to simulation. Let's do a model check. Hopefully there are no mistakes. Let's do a simulation check. If the numbers don't match with the frequencies that uh, were obtained in that video uh, reference, I'm going to change the A and B values, cross-sectional properties, cross-sectional dimensions. Okay, it's a fast process. It's done, and these frequencies don't quite match. Let's check this. Let me check that. I don't know. First one is 4.17. Yes, okay. So obviously they don't. I have to go and fix that at in the profile. So let's go to the behavior beam profile. Uh, I'm gonna make this thing 500 millimeter and this one 400 millimeters. Oops, 400 millimeters. Okay, and then we go back to scenario and run it. And then we're going to check. This, when the cross section is circular, it's not a big deal, but the cross section not circular, not tubular, you have to be careful with these directions 1, 2, and I did a kind of sloppy job. That's a lot better. In fact, you can see that if you keep 4.2, 9.9, yeah, 4.2, 9.9, 63, 2900, 63, 2900, etc. Now, if you want to look at the deformation, for example, displacement looks like that, but you can double click on it and then change the rendering to, in the third tab, change the rendering to not lines, but profile, apply. Yeah, that's a lot better. So there's the first mode. You can animate it. Yep. There's the second mode. This is the axial one. Probably this is the rotational one, etc. And these are in perfect agreement with the results obtained here. Okay, there's 16,700. Let's see which one this is. That's probably it's either this, yeah, it's like that. And the other one is going to be pretty much the same in the other direction, though. Now, see, these two are pretty much, yeah. Now, just keep in mind that uh, it shouldn't surprise you that these are the same numbers, pretty much the same numbers as those, and the reason being that it's solving the same solver, ABAQUS. Okay, and the differences are due to some minute issues that may not be available in one uh, implementation, but they're fairly negligible. All right, good luck. I'll do a few more of these with this particular type of structure and more complicated version of it later on.